Welcome to the deep dive. We're diving into string theory today
Always fun.
with this article called Is String Theory Inevitable?
Yeah.
Catchy title, right?
But
So,
this-
see, if string theory really is the answer to unifying physics.
The theory of everything.
Exactly, a theory of everything.
Yeah.
And
it's got some really interesting history in here, too.
yeah, I was going to say, the history part is kind of surprising.
Yeah, it's not what you'd expect.
Yeah, so, when you think of string theory, you think,
Unifying the universe.
right, unifying everything.
Yeah, but it actually started with something much, much smaller.
Oh, really?
Yeah, it came from physicists trying to understand the strong nuclear force.
Okay, so back up a little bit for me.
Sure.
The strong force, that's what holds the nucleus of an atom together,
Well,
right?
exactly. Yeah.
I got to be honest.
Yeah.
I remember learning about it, but it always seemed,
Kind of weird.
it did, mysterious,
Yeah.
especially compared to gravity or electromagnetism.
Right. It's definitely the odd one out.
Yeah.
See, those forces, they get weaker with distance.
Right.
The strong force, it's the opposite.
Really?
Yeah, the further apart you pull those particles, the stronger it gets.
So the more you pull, the stronger it pulls back.
Exactly. Like imagine two magnets stuck together.
Okay, yeah.
The harder you try to pull them apart, the more they want to snap back together.
Wow. So how did string theory come from trying to understand this weird force?
Well, there was this physicist, Gabriele Veneziano.
Okay.
He came up with an equation to describe the strong force data. It's called the Veneziano amplitude.
Okay.
And get this equation, it also described quantum gravity.
Wait, hold on.
Yeah.
Quantum gravity, that's
Mhm.
combining gravity with quantum mechanics, right?
Zig?
I thought that was impossible. Doesn't the math, explode?
It does. Or it did. See, the old attempts, they always got stuck with these infinities.
Yeah.
But string theory, through the Veneziano amplitude, it
Yeah.
avoided those problems.
It's like you found a loophole or something.
Yeah, like a secret passage between these two totally different areas of physics.
Okay, I'm starting to see why this was a big deal.
It was huge.
So, remind me.
Sure.
String theory says that everything is made of these tiny vibrating strings
Right, that's the gist of it.
instead of like point particle.
Exactly.
And the different vibrations make the different forces in particle.
You got it.
Okay.
Now this article,
Okay.
it goes even further.
Oh.
It says string theory isn't just a way to unify physics. It's the only way.
The only way. Wow.
Yeah, and they have this whole proof.
Okay.
3 steps.
Lay it on me.
First, they set up the rules for a good quantum gravity theory mathematically.
Right.
Then they say, look, the only solution that fits those rules is the Veneziano amplitude. And since string theory already uses that,
Yeah.
they conclude string theory has to be it.
Follow the math and you'll get string theory. Is that what they're saying?
Basically, yeah.
Sounds pretty convincing, gotta admit.
Yeah, until you look a little closer.
Oh.
See, this proof relies on some big assumptions.
Oh, okay.
And those assumptions are where things get shaky.
I was going to say, there's got to be a catch somewhere. Love a good assumption challenge.
Me too.
So spill the beans. What are these assumptions?
The first one is that a good theory of quantum gravity has to be complete and finite.
So no mathematical inconsistencies, right?
Yeah, no infinities, especially...
Like those other theories had.
Exactly.
So they're saying nature has to be mathematically neat and tidy.
Kind of, yeah.
I don't know, that seems a little presumptuous.
It might be.
Didn't we think some things in physics were impossible before? And then our understanding changed?
All the time.
So maybe complete and finite is a bit premature?
Could be.
What about assumption number 2?
Assumption number 2 is all about gravitons.
Gravitons. Those are the theoretical particles that carry gravity, right?
Right, like photons carry light. But here's the thing.
I knew there was a but coming.
What if gravity doesn't actually use particles?
No particles at all.
Maybe it comes from something deeper, something we haven't even thought of yet. Think of
that?
waterways.
Okay.
They're made of tons of tiny molecules, but we don't need, like, water quanta to describe them.
So maybe gravity is more like an emergent thing,
It could be.
not from a specific particle.
Yeah, maybe this whole idea of trying to find a graviton is the wrong approach.
Interesting. And what's the third big assumption?
The third one's even bigger.
Ooh, I'm intrigued.
They assume that gravity has to be a quantum theory.
Wait, so you're saying gravity might not even belong in the quantum world?
It's possible.
Like it's totally different from the other forces?
Completely different.
That's wild. So maybe trying to make gravity fit with quantum mechanics is just
A fundamental misunderstanding.
Whoa.
It's a crazy thought, I know, but it could be a huge breakthrough.
Okay, so we've got these three assumptions that the article uses to argue that string theory is inevitable.
Right.
But even if they're wrong, and string theory isn't the one,
Yeah.
does this article still tell us anything useful?
It definitely makes string theory look more likely, mathematically at least.
Okay, how so?
Remember that Veneziano amplitude, the one that connects gravity and the strong force?
Yeah, the magic equation.
Right. Well, it fits perfectly with their criteria for a good quantum gravity theory. And string theory is the only theory that naturally includes it.
So it's like string theory is in the right ballpark at least.
Exactly.
But not necessarily a home run yet.
Not yet.
We need more than just math, right?
We do.
There's a difference between a mathematical proof and reality.
There is.
So why is that distinction so important here?
Well, math can describe the universe beautifully, but it doesn't dictate what's actually true.
Yeah.
We've had plenty of elegant theories that turned out to be wrong.
So we can't just take the math at face value.
No.
We need evidence from the real world.
Experiments, observations, the whole shebang.
So where does that leave us? Is string theory still a contender? Or should we be looking at something else?
That's the big question, isn't it? And what about those other theories I mentioned?
Right, the alternatives. Like, what else is out there?
Well, there's one that's getting a lot of attention.
Oh.
It's called loop quantum gravity.
Loop quantum gravity.
Wow.
That sounds pretty cool.
It is pretty cool.
So what's the basic idea?
Instead of strings, it uses loops.
Loops?
Yeah, tiny loops that make up space-time itself.
So space and time are woven from these little loops.
That's the idea.
That's even weirder than strings.
It is pretty wild.
So instead of particles or even strings, we've got loops as the fundamental building blocks.
Exactly.
Okay, I think I'm following so far. And what does that have to do with gravity?
Well, these loops make space-time kind of chunky at the smallest level.
Chunky. What do you mean by that?
It's not smooth and continuous like we usually think of it.
Okay.
It's more like pixels on a computer screen.
So there's a limit to how small you can go.
Exactly.
Like you can't zoom in forever.
Right.
That's interesting. And how does that create gravity?
In loop quantum gravity, it's this chunkiness that gives rise to gravity.
So no graviton particle needed.
Nope. Gravity comes from the structure of space-time itself.
Okay, I think I'm starting to see the difference here.
Yeah.
String theory uses strings for everything, while loop quantum gravity focuses on the fabric of space-time.
You got it.
Do they make different predictions about the universe?
Oh, yeah, big ones, especially about the very early universe.
Wow.
You see, string theory, it usually assumes a big bang, right?
Yeah, the singularity, everything exploding from a single point.
Right, but loop quantum gravity has something else.
What's that?
It says the universe might have bounced.
Bounced.
Yeah, like a big bounce instead of a big bang.
Hold on, are you saying there was something before the big bounce?
It's possible.
Wow, that's
Yeah.
a huge idea. So we've got strings and gravitons versus loopy space-time and a bounce.
Yeah, pretty different pictures of reality.
They are. So how do we know which one's right? Can we even test these theories?
That's the tricky part.
Yeah.
They both deal with energies way beyond anything we can create in a lab.
Yeah, that makes sense.
It's like trying to study atoms by watching waves crash on the shore.
You need to zoom in way, way further.
Exactly.
So how do we even begin to test string theory or loop quantum gravity?
Well, we might not be able to create those conditions ourselves.
Yeah.
But the early universe did. So we can look for clues there.
Okay, so like looking back in time.
Yeah.
But how do we do that?
There might be traces of those early moments in the cosmic microwave background radiation.
The cosmic microwave background, that's like the afterglow of the Big Bang, right?
Exactly.
The baby picture of the universe.
Yeah.
So we could see hints of string theory or loop quantum gravity in that.
It's possible.
Wow, so the hunt for these clues is still on.
Oh, yeah.
This is why I love science.
Me too.
Always pushing the limits of what we know.
Always.
And this whole thing, trying to unify physics.
Yeah.
It shows us how much we still don't know.
It really does.
It's humbling, but also exciting.
Absolutely.
So, okay, we've talked a lot about this article and string theory in general.
We have.
What are the big takeaways here? What should we remember?
Well, first, even though this article argues for string theory,
Yeah.
it doesn't prove it.
Right.
There are other possibilities like loop quantum gravity. And ultimately, we need evidence to decide which one is right.
Evidence from the real world,
Exact.
not just math on a blackboard.
Nope.
So we have to keep an open mind.
We do.
And let the evidence lead the way.
Always. It's a great point. The physics community,
Yeah.
there's no consensus on string theory.
Right.
So are there other,
Yeah. What are the contenders?
Well, there are other approaches to quantum gravity.
Hmm.
One of the biggest ones is called loop quantum gravity.
Looped quantum gravity, huh?
Yeah.
That sounds interesting.
It is. It's pretty cool.
So how's it different? What's the main idea?
Okay, so instead of tiny strings,
Yeah?
loop quantum gravity imagines space-time itself as being woven from these tiny loops.
Tiny loops, huh?
Yeah.
Like a fabric of reality or something?
Yeah, kind of like a quantum fabric.
So it's not even particles anymore.
No.
It's not strings, it's
loops.
Loops. The fundamental building blocks of reality.
That's the idea.
Man, physics is wild.
It is, right?
Okay, so space-time is made of these loops.
Right.
And how does that connect to gravity?
So one of the things these loops do is they make space-time granular.
Granular.
Yeah, like at the smallest scales.
Okay.
It's not smooth and continuous.
Right.
It's more like it's made up of these little chunks.
Chunks of space-time, like pixels on a screen or something.
That's a good analogy, yeah?
So there's a limit to how small things can get. It's the exact.
Wow, okay. And this chunkiness, this is what causes gravity.
In loop quantum gravity, yeah.
No need for a graviton particle.
Nope, gravity emerges from the structure of space-time itself.
Okay, so I think I'm getting the difference now.
Yeah.
String theory, it's all about the strings.
Right.
Loop quantum gravity is about space-time itself.
Yeah, it's about the fabric of reality.
The fabric of reality, I like that.
And they make some very different predictions.
Yeah, like what?
Well, one of the biggest differences is how they describe the very, very early universe.
Oh, okay.
String theory, like a lot of theories, it usually starts with a Big Bang, right?
Right, a singularity, everything exploding outwards.
Yeah, but loop quantum gravity,
Yeah.
it offers a different picture.
Intriguing. What is it?
It suggests that maybe, instead of a bang, the universe bounced.
Bounced?
Yeah, like, imagine the universe collapsing in on itself.
Okay.
Reaching this point of extreme density and then rebounding outwards.
Yeah.
So a big bounce instead of a big bang.
Exactly.
What does that mean? Like there was something before the bounce.
That's one of the big questions, yeah.
Wow, that's a big one.
It is. It's really fascinating.
Okay, so we've got string theory, we've got loop quantum gravity.
Two very different ideas.
They are.
Yeah.
The question is,
Yeah.
how do we know which one's right?
How do we test these things?
Exactly.
It's tricky. See, they both deal with these incredible energies.
Yeah.
Energies that are way beyond anything we can create.
Right.
In a lab, I mean.
Yeah. We're not going to build a Big Bang anytime soon.
Not anytime soon, no.
So how do we even approach testing these theories?
Well, we may not be able to make those energies ourselves, but the early universe, it had those energies.
So the early universe is like our laboratory.
In a way, yeah.
Okay, that's clever.
So we can look for traces?
Traces?
Yeah, traces of those early moments.
Where would we even look for those?
One place to look is the cosmic microwave background radiation.
The cosmic microwave background.
Yeah.
Right, the afterglow of the Big Bang.
Exactly.
The baby picture of the universe.
Yeah, and it might contain hints of string theory or loop quantum gravity.
Wow, so we could actually see the effects of these tiny strings or these loops.
It's possible, yeah.
By looking at this ancient light?
Yeah.
That's incredible.
It is. It's amazing what we can learn.
It really is.
From the universe.
So the hunt for these clues continues.
It does.
This is what makes science so cool.
Oh, I agree.
It's always pushing the boundaries.
Always.
And this whole idea of unifying physics,
yeah,
it really shows us how much we still don't know.
It's humbling, isn't it?
It is. It's humbling, but it's also exciting.
It is exciting.
It's like we're just scratching the surface.
We are, yeah.
So, okay, let's bring it back to this article.
Sure.
And this whole conversation about string theory.
Yeah.
What are the key takeaways here?
Well, I think the big one is that even though the article makes a strong case for string theory, mathematically, it doesn't prove it.
Right.
It doesn't mean it's the only answer.
Okay.
There are other possibilities out there like loop quantum gravity.
Right.
And in the end, it's going to come down to evidence.
Evidence from the real world.
Exactly.
Not just equations and theories.
Not just theories, yeah.
So we got to keep an open mind.
We do.
And see where the evidence leads.
That's what science is all about.
It really is amazing to think how much we've learned
It is.
about the universe, about galaxies and particles and all that.
Yeah.
But it's also kind of mind-blowing how much we still don't know.
It is.
Like this whole conversation
Yeah.
about unifying physics, about quantum gravity,
Right.
it really hits home that there's so much more to discover.
Oh, yeah. We're just getting started.
And I think one of the most fascinating things is that it makes us really question our assumptions.
Absolutely.
Like assumptions that we thought were like fundamental.
Yeah, the bedrock.
Yeah. Like that third one we talked about.
Right.
That gravity has to be a quantum theory.
Yeah, what if it isn't?
What if it isn't? That's huge.
It is.
To think that gravity might be totally different
Totally different.
from the other forces, like what would that even mean?
Well, it would mean that a lot of our current thinking about unifying physics might be off track.
Off track? How so?
Instead of looking for one big unified theory where everything fits together perfectly, maybe we need a different picture.
Different how?
Like, imagine instead of one big puzzle, we actually have two separate puzzles.
Two puzzles? Whoa!
One for the quantum world.
Okay.
And one for gravity.
So gravity is just, like, doing its own thing.
It could be.
It's almost like we've been trying to jam them together.
I know, right?
But they don't even belong together.
Maybe gravity has its own set of rules.
Its own rules, wow.
Totally separate from the quantum world.
Man, that would change everything.
It would, wouldn't it?
It's like, we've been looking for the missing piece.
Yeah.
But we've got the wrong puzzle box.
Exactly. And who knows, maybe that's the key.
To what?
To unlocking an even deeper understanding.
Of the universe, of gravity. It's like we're discovering a whole new continent.
I love that analogy.
Yeah. Like there's this whole other world out there with its own laws, its own everything.
Yeah, and we're just starting to explore it.
That is so cool.
It is. It's mind-blowing.
So we've talked a lot about string theory.
We have.
About loop quantum gravity.
Yeah.
About all these crazy ideas.
It's been a journey.
It has. But let's bring it back to the article. And the main point here.
Yeah, what are the takeaways?
What should we remember from all this?
Well, I think the biggest thing to remember is that even though the article makes a good argument, it's still just an argument.
Right.
It doesn't mean string theory is definitely right.
Okay.
Or that it's the only way.
We need more than that.
We need
evidence from the real world to back it up.
Otherwise, it's just a nice story.
A nice story, yeah.
And we need to be open to other possibilities.
Right, like loop quantum gravity.
Exactly, or something we haven't even thought of yet.
Something completely new.
Who knows what's out there?
That's the exciting part. There's so much more to discover.
There is, and that's what keeps us going.
It does. It really does.
The curiosity, the drive to understand.
And the fact that we might be wrong.
Oh, yeah, that's always a possibility.
That's what makes science fun.
I agree. You got to be willing to be wrong.
Absolutely.
To learn something new.
So, to our listeners out there.
Yeah.
Keep asking questions. Keep exploring.
Keep that curiosity alive.
And don't be afraid to challenge the assumptions.
Yeah, the assumptions.
Even the ones that seem like fundamental, because you never know what you might find.
You never know.
So keep diving deep. Keep learning.
And keep an open mind.
Until next time on The Deep Dive.